Hello and welcome back to yet another video on axiomatic thermodynamics, and today we are going to look at yet another cyclic process, which is the Stirling process. We have already talked about it in earlier videos, that it has a bit more realistic approach as compared to Carnot's process. And in this video we are gonna basically talk about a bit of the process. We are not gonna go very deep into derivations of different values of the cyclic process, but we are gonna just try to motivate it. Right, we are gonna start maybe with a bit of a recap. We watched in the last video about the Carnot process, which was basically having isothermic and adiabatic processes in it. However, we also did see that adiabatic processes are a bit difficult to realize in reality, because adiabatic processes basically do not let energy transfer happen between a system and the surroundings. So basically the boundaries are innate to energy transfer, and that would mean that there must be a lot of engineering that goes into building such a boundary, which is not simple. So right, and that's why we have the Stirling process now, which is basically having isothermic and isochoric processes. Isochoric, on the other hand, basically has the volume constant of a system. And we also saw how the efficiency of machines is defined. It is defined as the work done divided by the heat that is given into the system. And it can also be written as the difference of the two temperatures divided by the temperature of the state when it is receiving heat from its surrounding or a heat reservoir. And obviously this can be also derived from the values of delta W and delta Q in the respective processes within the Carnot's process. And right, and the Carnot's process efficiency will always be less than 1, or actually also equal to 1 in ideal cases. So I should also write maybe an equal. And we also talked about a bit on a pump, on an idealized pump, whereby work done on the system leads to the change of heat energy out of the system, and that then has a reciprocal efficiency of a Carnot machine, and it is greater than 1. Right. Now that we are speaking about the Stirling process, the Stirling process has, as we said before, as compared to the Carnot process, isothermic and isochoric processes, and it is also a cyclic process. And it was devised in 1816, actually before Carnot did his work, by a Scottish clergyman and engineer, Robert Stirling, with also the help of his brother. Here is the person. He obviously also got inducted into the Scottish Hall of Fame recently. Right, and this image is also taken from Wikimedia. So yeah, hats off to them for doing great job in collecting pictures of scientists and personalities over the years. Now we are gonna talk about the phase diagram of the Stirling process. And it looks, as you have seen, a bit different as compared to the Carnot process. You still have the isothermic parts of the plot, but instead of the adiabatic parts of the plot, you now have the isochoric ones, which are given by the blue lines. And you again have 4 points, which we will also be looking at with an example. And this time I obviously also did not write the T2 equals T3 and T1 equals T4. Rather, I just mentioned that there is a higher temperature above as compared to temperature below. And this area basically is a heat reservoir which gives heat into the system. and then on the other hand you have a cooler reservoir where you give the heat energy back into the surroundings. Right, if we analyze this now as with the help of a diagram of such an engine, of a Stirling engine, let's say, we see that in the beginning we have so this is basically part 4 to part 1, whereby we see that an ideal gas is compressed and it is cold, and right now it is receiving heat from a heat reservoir, which is denoted by the red, and the colder reservoir is then on the left with blue. Right, so it's a machine whereby compressed cold gas, ideal gas, will receive heat from a heat reservoir and get hotter. So this is basically, this happens in the same volume, which is basically denoting this part of the phase diagram, and we see that it happens in the same volume, and the temperature increases from Tc to Th, and it is denoted for that the gas moves from blue to red, which basically means it becomes hotter. And then it starts to expand, because now it's hotter as compared to before, and now the kinetic energy of the individual particles inside the mixture of ideal gas starts to expand, because now it has higher kinetic energy and it goes up, and because of this there's a change of volume from this part to this part, and this basically signifies this part of the curve whereby the volume does change. And at the same time, the hotter particles, they have now a larger volume, and given the same temperature that it has, it will obviously now try to lose the temperature, because it has a larger volume. It doesn't really need that much volume anymore, and it will try to exchange heat with the colder reservoir. Right, what happens with that? Obviously we get a colder gas again, and now the gases, they have reduced kinetic energy. What should they do? They do not need that much volume anymore, and they would go from here exactly to this part again, because as we see, from moving from here to here, it happens in the same volume, so it should be actually an isochoric process, which is basically this part of the diagram. And then you have a volume change from here to here, and that would be defined through this part of the diagram, which also shows a decrease in volume, because volume is on the x-axis, and you see that it then gets compressed because the colder gases now have less kinetic energy. Yep, so this is what all I wanted to tell you about the Stirling process. It is again how the gears work in cars, and like in an ideal car, the gears would work in this way, and it is basically an idealization. It is a realization of the ideal Carnot process as much in a practical way as possible. And this was again a huge thing in thermodynamics back in the days and in the Industrial Revolution. So it is actually of great importance to the entire theory of axiomatic thermodynamics. Right, I hope I could shed a bit of light onto the topic, and help with any kind of doubts if there were. And right, if you enjoy the video and if it helped you, please like it, and also share it with your friends so that others can also get helped. Please also drop in the comments if there is anything that you would like to have changed as in a constructive as form of a constructive feedback to me, so that I can change them in the next videos. Right. Thank you again for listening. We meet again in the next videos.